Good evening, and thank you very much for coming to the latest installment of the SLAC Public Lectures. This evening, our talk is by Johanna Nelson-Wecker, actually a new staff member here at the laboratory. Johanna did her PhD at Stony Brook, and her expertise is X-ray microscopy. How do you take a micrographic picture with X-rays and get rid of all those lenses, which are really very difficult for X-rays, and get down to the sub-micron scale in terms of being able to visualize things. She did a lot of her graduate work at Berkeley, at the Advanced Synchrotron Light Source, at Berkeley, yes? At the Advanced Synchrotron Light Source. And I asked her, did you work on batteries? And she said, no, I worked on yeast. But it's fine. That leads naturally into this, as you'll see. And you're going to get a whole new experience of what those batteries are doing in your cell phones and laptops from this lecture. So let's welcome Johanna to hear about the secret life of batteries.
Thank you. Thanks. How many of you have a battery on you right now? I do. How many of you could explain to your neighbor how that battery works? Be honest. Maybe. Iffy. Okay. How many of you are frustrated when your cell phone dies before the end of the day? Exactly. So we all want better batteries, right? One last question. How many of you drive an electric vehicle? A few. It's pricey, but hopefully with this research, we can make it more affordable for everyone. So today I'm going to talk to you about batteries, and I'm going to talk to you about how using X-rays we can learn more about batteries, and with that knowledge we can make better batteries. So we are going to first start with explaining how batteries work, so we're all on the same playing field, and then why we need better ones and what we need to improve about them. And then we're going to get into the real science, and I'm going to show you movies of batteries breathing, expanding and contraction, cracking, and then eventually failing. And we're also going to watch the chemistry happen. And we're going to do both of those things using X-rays. And then finally, we're going to take it all back, figure out what we learned, figure out how we can apply that to make a better battery. So what's a battery? They come in all different shapes and sizes, even potatoes. You can make a battery out of a potato and run a clock on it if you'd like. The two main components, or two main types of batteries, are rechargeable and single-use batteries. Rechargeable batteries are more expensive, but you can use them again and again. And so they're useful for things that are used frequently, like your cell phone, your laptop, power tools, the lead-acid battery in your car, and the batteries that are all in electric vehicles as well. Single-use batteries are much cheaper, but they only work once. But they're very reliable, so they're very good for a low current over a long period of time. And so they're good in batteries, in flashlights when you need it instantly and you don't want to have to recharge your batteries of your flashlight before you can use it. In your smoke detectors, for example, also that potato is a single-use battery. You'd have to change the potato if you... And then the normal batteries you have. So the two main differences are, do you recycle it after you used it once, or can you plug it in and recharge it? We're going to mostly focus on rechargeable batteries because that's what we're going to use in electric vehicles. But how does a battery work? And so I'm going to use the potato battery as an example. You need three things. You need two electrodes of two different types of metal. For the potato battery, it's usually copper and zinc. So you can use a nail or a penny. And then you need your electrolyte, which the potato provides. It's actually phosphoric acid inside the potato that's going to be allowing the battery to work. And so if you assemble your potato battery like this, you should be able, if you attach the electrodes with a piece of metal, get a current across it. So if we look at it schematically, we still have our two electrodes, zinc and copper, and they're in a bath of electrolyte, that potato. Right now I have not connected the battery, so it's open here, and there's a potential across it. But if I close the battery, then we'll start discharging. So I'll close the loop and we can light a light bulb, for example. And there's two things that are happening. One, electrons, which are negative charges, are going across the wire through our light bulb and lighting our light bulb. And those electrons cause the ions, and remember that an ion is a positively charged atom. So basically you've taken off two electrons from our zinc, and those ions go through the electrolyte. So I'm going to play that again. So the ions go through the electrolyte, and the electrons go through the metal wire. And they meet up again in the other electrode. What if we want to recharge this battery? Potato batteries don't recharge, but assuming we could recharge the battery, the electrons would go back through the metal, and the ions would pass through the electrolyte again, and they would go back to the original electrode. Now, the way we like to plot what's going on in a battery is in a CV curve, and it's a capacity versus voltage curve. Here, if you know anything about capacity, here is a gravimetric capacity. So it means milliamps, which is a current, times hours, which is time, over grams, which is the weight of the material. So as we discharge the battery, you're going to see this little red dot. It's going to go through the voltage. So it's going to lower its voltage as you take capacity out. And then during the charge, we're going to gain voltage back as we charge up the battery. So you're going to see a lot of these CV curves in the next hour. And so this is the basic way it's working. So you now have a vague idea of how batteries work. Why do we need better batteries? Now, everybody needs a better battery for their cell phone and their laptops just because it's convenient. But the real hard batteries to make are batteries for electric vehicles. But why do we want to electrify vehicles? So here are three plots, and this is the x-axis is time, thousands of years, and present is right here. And the first plot is the global temperature. Second plot is the CO2 concentration in the atmosphere. And the third plot is the sea level. And you can see right here, I've circled the CO2 concentration over the last 10 years, 25 years, and you can see it is skyrocketing. If we zoom in, and this is from 1960 to present day, you can see the CO2 concentration in the atmosphere is steadily rising. And if we looked over time, the global temperature is following the CO2, and same with the sea level. So if we see that the CO2 concentration is skyrocketing, we can pretty much expect that the global temperature is going to also increase, as well as the sea level. And we see that as well if you look over in the last few years. So this is 1880 to present day, and you can see that the global temperature is starting to rise. And this is 1992 to present day, and this is the sea level, and it's also starting to rise. And because sea level is rising, we know that the ice caps are melting. And so these are outlines in yellows of the median ice cap from 1979 to 2000, and then from 2005 minimum, and then 2007 minimum. And if I plotted more recently, it'd be even smaller. So clearly we have too much CO2 in the atmosphere. So we need to turn to cleaner energy sources. So instead of using fossil fuels, we need to use things that do not produce any CO2, like wind, solar, and other things like nuclear and geothermal. But if we turn to using cleaner energy sources, we need to think about what we use the energy for. So this is just electricity, which is easy to convert, well, relatively easy to convert. But there's a large pie section for transportation. And it's not as clear on how you would convert clean energy to use in transportation. It's pretty inconvenient or just ridiculous. So we really need to think about storing our clean energy into a battery. So we can take our clean energy, store it into large batteries, and then we can put those batteries into a car and then plug our car in when we've run out of charge. And so that's why we really need to improve these batteries. So in 1991, there was a big breakthrough in battery technology, rechargeable battery technology, and that was with the lithium-ion battery. And it revolutionized the portable electronics device. So we went from gigantic purse-sized car phones to our iPhones of today. So here is a plot of different types of batteries and specific power on the y-axis and specific energy on the x-axis. So specific energy means that we can, if we go along the x-axis, we can get more miles from our electric vehicle with the same amount of weight. If we go up the y-axis, we can get more acceleration with the same amount of weight. Ideally, in an electric vehicle, you want lots of miles, lots of acceleration. So we want to go up the diagonal. Lead-acid battery, what you have in your car right now, is down here. And we've progressively switched to nickel, and that's improved our mileage as well as our acceleration. Lithium-ion batteries are up here. Lithium metal, which has the potential to work, but it is currently very hazardous, is even better. If we continue up this plot, however, we can compare it to fossil fuels. And this is really what our target is. Fossil fuels are way up here, so we've got a long way to go if we want to get up to fossil fuels. So we basically want to force our way up this slope so that we can make a vehicle that's electric, that's going to run like you expect a vehicle to run. And since the 1990s, since we invented lithium-ion batteries, there's really been only incremental improvements on rechargeable batteries. So we really need a scientific breakthrough that's going to help us go from here all the way up to here. So currently, where are we standing in electric vehicles right now? The range is from 70 to 165 miles per charge, which is getting better every day. Unfortunately, the 165 is a Tesla, and really what they did is just eliminate the trunk space. So you are carrying a large volume of batteries. The battery life, however, is actually really nice. We can run 200,000 miles on a single battery, and maybe even more. So we're really actually quite good on that. However, charge times, if you own an electric vehicle, you realize that you typically charge overnight or when you're at work, because charge times take from 6 to 12 hours, ideally. There are now fast charging stations, which take 15 to 30 minutes. If I owned an electric vehicle, I would not use them. Knowing what I know about batteries, it's not a good idea. I would do it in an emergency, but that's it. Finally, the cost. If you compare a Ford Focus that's electric, and that's the base model, compared to a similarly equipped non-electric Ford Focus, the difference is $12,000, and that's just the battery. So we really need to lower the cost so that everyone can afford an electric vehicle. So these are the three things that we really need to work on. The focus of this talk is trying to improve the range and trying to improve it without reducing the battery lifetime. And that's a difficult thing to do. So we want to look for a new anode material. Here's a plot of the capacity, how much range you can get from a single charge, and different materials. Currently, we use carbon. The best material we can think of is pure lithium metal. However, it's flammable, and it causes issues. All of those problems with Airbuses catching fire, Teslas catching fire, computer batteries catching fire, that's 10 times worse if you use pure lithium metal. So people are working on it, but it's very tricky. So the next best thing is to use alloying electrodes. Now an alloy is just a mix of metals. So you can have either of these three metals. Silicon, which has the best, it's about 5 times higher capacity than the carbon that we use now. Germanium, which is about 4 times higher, and tin, which is only about 2 times higher. Now those alloys means that these metals are mixing with lithium and forming an alloy during the battery charging and discharging. And you can also see that if you look on the periodic table, they're all right down the same column, so they kind of make sense. You get worse capacity, the heavier the material is. So silicon would be the best material that we want to look at. So as I said, they're alloying materials. So if you take any of these metals, silicon, germanium, or tin, and you start inserting lithium metal into the metal, you form an alloy of lithium and that metal. And it has a large capacity. It stores lots of lithium ions. But there's also this large volume change. As you're putting lithium ions in, your whole structure is expanding. That can cause issues. It can cause cracking and fracturing in your material. So this is actually one of these metals. It used to be a film that was very smooth, and this is after cycling. You can see there's giant cracks in it, and it's been compared to a dry lake bed. So we want to be able to reduce these cracks and fracturing because they're limiting the battery lifetime. So we can get this really nice capacity. We can drive our electric vehicle really far compared to what we can right now, but your battery is only going to last 500 cycles maybe. You're going to have to buy a new battery every year. So for the rest of the talk, we're going to study germanium. And I said that silicon was the best. And germanium's a little heavier, so it's not as good capacity. But with X-rays, it was easier for us to see germanium than it was to see silicon, and so we chose that. And it also represents all of these materials, tin, silicon, and germanium. So if we know something about germanium, we can hypothesize about silicon as well. Unlike silicon, it has a large lithium-ion mobility. Lithium ions can move very easily in germanium, and also electrons can move very easily in lithium. Silicon, on the other hand, it's a pretty good conductor. It's a pretty good insulator. So what we think is happening in germanium as we insert lithiums, here's some germanium particles. We're not really sure what happens while we're inserting lithium, so we really want to know what's happening right here, what chemistries are happening, but we know they expand. We're not exactly sure what lithium-germanium alloy we have, so we really want to figure that out after we've inserted all the lithium that we can. And then when we take out the lithium, we're really not sure what chemistries are going on as we're taking out the lithium. But we do know that after the lithium's been taken out, germanium particles are fractured. Maybe pieces have fallen off. So we want to explore the chemistry, and we want to explore the changes in size, cracking, and if the particles break apart. To do that, we're going to use X-rays, and we're going to use 3 different techniques. We're going to use X-ray imaging using a microscope. We're going to use X-ray diffraction to look at the crystal structure. And we're going to use X-ray absorption spectroscopy to look at the chemistry. And with all 3 of these structures, all 3 of these techniques, we can really get a complete picture of what's going on. And we're going to use X-rays because X-rays are very good at seeing inside things. You can see bones inside your hand if you go to the doctor's office. You can see inside suitcases when you put your luggage through the X-ray scanners at the airport. So we want to do a similar thing, but look at very, very small parts of the battery. And to do that, we're going to have to go to a synchrotron. So this work was done at Stanford Synchrotron Radiation Light Source. And the great thing about a synchrotron is it produces extremely bright X-rays. So it's your doctor's office machine times 1,000,000. This is a night view of the synchrotron, which makes it look pretty. This is a more realistic view of the synchrotron from the top, and there's a booster ring where the electrons are sped up, and a storage ring. We take the electrons from the storage ring, and they produce X-rays. I'm not going to go into how that happens, but we get really bright X-rays from it. And I said we're going to look through a battery, and we're going to look through a battery while it's operating. And so we need an X-ray transparent battery. I'm going to pass around 2 examples of batteries. Now, they're not really batteries because I've taken out the flammable lithium metal and the toxic electrolyte, just in case someone decides to take them home. But they're an example of what our batteries look like. And there's a picture of it here in case you're too anxious to get it passed to you. And here's a schematic of it. We can pass X-rays through it. And all of the components are here. We have a current collector, which is going to provide that electrical contact between the 2 electrodes. And that's shown here. We have lithium metal, which is right here in the picture. We also have the electrolytes soaked in this separator, and the separator is this plastic piece right here. The separator prevents the 2 electrodes from touching and causing a short circuit, which is very important. We want the electrons to go through the current collector, not directly from one electrode to the other. And then we have the counter electrode, the other electrode that's not lithium metal, which you can't see in this picture. It's on the other side. And then finally, this polymer polyester film, and it's just a bag. It's very similar to the bags you get electronics in, except that it's not aluminized. Now, I said we wanted to image batteries while they operate. The easiest way to image things or investigate things is when they're dead and cut apart. But that doesn't really tell you really much about the object. So the next best thing is to study your frog inside an aquarium, so you can see it living, breathing, eating, but it's not really in its natural environment. So we really want to study batteries in a natural environment. We want to study them while they're cycling extremely realistically, and that's our end goal. We want to make a documentary on batteries. So the first technique we're going to use is X-ray imaging. It's a microscope. So we're going to be able to look at microscopic material inside our battery. We're going to be able to look at these germanium particles that are on the micron scale. So here's a picture of the microscope. This is the SSRL director. He sometimes visits the microscope. It doesn't really look like a visible light microscope that you'd have in science class, but it works very similarly, except that it uses X-rays. Simona Mistra did some of the work on the early work on this battery, but he's now working at BASF in Germany. And then here is a close-up shot of the microscope, and this is our battery right here, and you can see there's 2 electrodes that are connected. I said that we were going to be imaging things on the micron scale. And so here's a picture of germanium. The bright particles are germanium. And this is a scale bar that says 5 microns. Now, the human hair is 40 to 80 microns, and a red blood cell is about 6 to 8 microns. So that gives you an idea of how small this is. So as we put lithium ions in, these particles are going to start to fracture. They're going to start to crack. And then as we add more lithium ions, they're actually going to start to expand. And the cracks are actually going to fill in because you're expanding. And then when we take out lithium ions, the particles are going to shrink. And as we completely remove all of the lithium ions that we can, we're going to end up with not a material that looks like this, but it's going to be spongy. It's going to be porous. So I'll show you the movie now. And there's going to be a dot that's going across that can tell you where you are on the CV curve. So you can see not much happens at the very beginning, but once you reach this plateau here, see the particles are expanding, they're starting to crack. The cracks actually fill in. And then as we remove the lithium ions, the particles contract and you end up with something very porous looking. It doesn't look like what it originally looked like here. So I'll play it again, just so you can watch it. So this is germanium particles inside a working battery. That was the first cycle. We can also look at the second cycle. And in the second cycle, what we see, and I will show you in a second, is that only this large particle is going to expand and contract. All of the small particles up here and the particles down here are no longer expanding and contracting. And that's really quick, so I'll play it again. So only that large center particle is expanding and contracting. And that's really important because all of the small particles are no longer having lithium ions inserted into them and taken out. So they're no longer participating in the battery's capacity. So we're losing capacity. And we looked at a lot of different locations in the same battery. And what we found is, this is particle size, this is area over here. Most of the small particles are green. They're inactive in the second cycle. They were not participating in the second cycle. But the large particles are still participating in the second cycle. They're still expanding and contracting in the second cycle. Luckily, 90% of the volume is in the two largest particles. So that really only means that we've only lost about a quarter of the capacity after the first cycle. But that's not what we want to do. We want to maintain capacity as we cycle it multiple times. And this is one of the reasons why we're not getting 2,000 cycles in these batteries, because we're not able, we're losing all of the capacity of the small particles. So what we think is the reason why the small particles are not active in the second cycle, but the large particles are because the large particles have a larger surface area, and it's just probability. So it's a higher probability that they'll stay electronically connected. So something I didn't really tell you yet is that these germanium particles aren't sitting directly on the current collector, on this metal that conducts electrons. They're actually inside a conductive matrix. And the electrons have to move through the conductive matrix to reach the particles. So as you add lithium ions, the particles expand, and the conducting matrix also gets pushed out. But as you remove lithium ions, the matrix doesn't necessarily contract with the particles, and so you get these voids around the particles, but you're more likely to have some connection with the conducting matrix if you have a large particle versus a small particle where these electrons can't reach the small particle because it's no longer connected. So that's what we hypothesize is happening inside the battery. To fix this, what we want to do in the future is use a self-healing polymer, essentially that's a glue that's going to keep our small particles together. So there's a group at Stanford that's developed this polymer where you can pull it apart, you can break it, and you can put it back together, and it stretches just as if you hadn't broken it. So we want to try to use this glue so where we have large particles that expand, but the glue, which is in pink, heals all of the particles and sticks them together after they've contracted, after the lithium ions have been taken apart. So another thing that we can do with our microscope is to take CAT scans. So we can take 3D images of materials. And a CAT scan is exactly like you get in the hospital, where a patient sits on this table and there's an X-ray source and an X-ray detector that go around in a circle here. And you can collect 2D images at many different angles, and there's computer algorithms that put those images together into one 3D image. Now, we can't rotate our synchrotron, so we rotate our sample, but in the hospital, you really don't want to rotate patients. So they don't. So we rotate our sample and collect an image at different angles. And you can see that at different angles, these 2D images look very different, but if you put them into a computer algorithm, you can get a 3D object out. And so we can do that with our battery. And so we did. So we looked not as we were cycling, but before we cycled, after we put lithium ions in, and after we removed those lithium ions. And this is the same two particles in time. And they're 3D, so we can rotate them. And because we have a 3D volume, we can actually calculate how much expansion we have. We have about a 320% expansion, which is really close to the theoretical. And you can also see that when you've added lithium ions, it seems like there's some cracks here. And actually, if you remove the lithium ions, you can actually see that those cracks have fractured the particle into 3 independent pieces. And so we now have evidence that these big particles are fracturing into small particles, and these small particles are no longer connected to each other. Now I have to fight. So moving on to our next technique. We learned a lot about what the particles look like, how they fracture, how they expand, contract. But now we want to know what the chemistry is. What alloys are we forming with this germanium and lithium metal together? And so the first technique we're going to look at for looking at the chemistry is X-ray diffraction. And that specializes in looking at crystalline material. So this is what the X-ray diffraction setup looks like. X-rays come from here. This is our battery again, right there. And the data looks like this, and it's sitting, I've actually projected it onto the imaging plate, so it doesn't really look like that in real life. But on the computer, it looks like that. And Nian Liu is helping with making the batteries. He's a Stanford graduate now. He's just graduated. So a quick theory about what X-ray diffraction is. If you take X-rays and you shine them onto a material that's very crystalline, and crystalline means that the atoms are regularly oriented, so they are evenly spaced in a very structured environment, you get a scattering pattern with bright spots everywhere. And this diffraction pattern is unique to the crystal structure. It tells you where the atoms sit. If you, instead of a single crystal, you have lots of little crystals randomly oriented, instead of bright spots, you get bright rings on your diffraction pattern. But they also tell you something about where the atoms are situated. So we can tell what sort of crystal structure we have and what sort of chemistry we have inside of our battery. So to take that data, which are rings, concentric rings, you want to analyze it and make it into a 1D plot or 2D plot. So you notice that all of the rings are centered, and you can just look at a specific radius, and the intensity is the same everywhere around it. So if you take a specific band and just add up all of the intensities, you can get a plot in Q space, which is basically similar to the R, the radius going outward. So these are small circles, these are large circles. And all of these different peaks you can identify, and it will tell you something about your material. So this is the actual germanium battery, and I've only taken a small section of the diffraction peaks because there's lots of them. It's a little hard to tell maybe between the purple and the blue spots, but these two purple peaks are from the plastic pouch. So an annoying thing about having a real battery is you have crystalline material from things that you don't actually care about, so you just have to deal with them. And then we have a little tiny germanium peak, which is the peak we actually care about. So we're going to look at how this germanium peak evolves as we add lithium ions and then remove them. And we're also going to see, are there other peaks that are forming other places? So this is an extremely busy plot. But the plot that I just showed you is the first one down here. And as you go up the plot, we are in black, adding lithium ions, and then the red ones are removing lithium ions. And I've identified different peaks, either germanium peaks in blue or lithium-15 germanium-4, which is a lithium-germanium alloy, in green. So the first thing you see, starting from the bottom, as we add lithium ions, the germanium peak starts to slowly disappear. So we're gradually losing crystalline germanium, which is what we expect. We're putting in lithium ions. We should be forming some sort of alloy. And eventually, but there's this big space here, these lithium-15 germanium-4 peaks appear in green. And that happens near the end of our cycle of adding lithium ions. When we start removing lithium ions, those 3 peaks start to gradually disappear. And interestingly enough, this germanium peak doesn't reappear. So we aren't reforming crystalline germanium. So we already know we're doing something to this battery that's not reversible. And we want a rechargeable battery when we want everything to be completely reversible. So we already know this is a bad sign. But there's a lot of blank spots in here that we don't know what's going on. So we know at the beginning we have crystalline germanium. We don't know what's going on around here. But then we get lithium-15 germanium-4, which is really nice. That's a lot of lithium ions for a few germanium atoms. And then we don't know what's going on as we remove lithium ions, because we see no extra peaks. But remember, X-ray diffraction only shows us what's crystalline. It's only going to show us crystalline material, regularly ordered material. All of the other materials that we're forming in these blank spots must be amorphous. So they don't have regularly ordered atoms. So we need another technique if we want to really understand the chemistry everywhere else. And so that's where we're going to the last technique. And this is X-ray absorption spectroscopy. And that's going to tell us more about the amorphous material, the non-crystalline material. So this work was done by Linda Lim. She's also a Stanford graduate student. There are 2 detectors of X-rays, and then you put your sample in between, so your battery's sitting here, and very similar to how the other setups were, the batteries look very much the same. You've got your 2 electrodes connected, and you can cycle your battery. So what information do we get from X-ray absorption spectroscopy? First of all, what is X-ray absorption spectroscopy? So it relies on the fact that every element in the periodic table absorbs X-rays very well at a specific energy. So materials absorb X-rays at any energy, but at specific X-ray energies, they absorb them very well. So there's a very big jump in their absorption, and that's very specific to the actual element. Around this large jump in absorption, there's all these wiggles. All of that information can tell us about the chemistry and the structure of the material. And so we're going to use all of those wiggles to tell us what's going on in the battery. How do those wiggles actually form? So if we have our specific atom that we're interested in, we're tuned, we've changed our X-ray energy so that this atom absorbs very, very well, and then there's surrounding atoms here. If you hit that specific atom with an X-ray that absorbs very well, electrons scatter off it, and we can think of them as waves. And so it's a circular wave going out, which will hit other atoms that are surrounding it, and they will bounce the wave back. And that information, if we can collect it, will tell us about these atoms that are surrounding the atom that we actually hit. And it's very similar to dropping rocks in a puddle. You've got circular waves going out, and they can interact with each other, and they produce little waves in our absorption pattern. So this information can tell us about the neighboring atoms. How many atoms are there? It can also tell us what type of atom they are, what elements they are, how close they are, what's the distance between the atom we hit and the neighboring atoms. And the best thing is it works on amorphous materials. So it can work on glass, it can work on liquid, it can work on our germanium lithium alloy that we don't know what it is. So this is the actual data that's analyzed. And I just want to show you very quickly that there's pretty much 3 big bumps this hump here, and this hump here. And this, again, is during cycling. So the black is when we're adding lithium ions, and the first one is over here, and as we go towards you, we're adding lithium ions, and then the red is when we're removing lithium ions. You can see that this large peak at the beginning drops down, and then sort of becomes nothing, wiggles, more noise, and then it kind of starts to reappear at the very end. These little peaks here pretty much disappear after we start cycling the battery. So it's pretty noisy data, but we think we can get some information about it. This first peak tells you about the nearest germanium atoms to the germanium atom we hit. So it tells you the nearest germanium distances. The second peak tells you about the second nearest ones, and the third peak tells you about the third nearest ones. The shapes and the size of these peaks are going to tell us about these atoms. I'm not going to go through the nitty-gritty details of the analysis. I'm just going to tell you the results. So we already knew that we started out with crystalline germanium. What we found out now is that the next thing we have is amorphous lithium-7 germanium-2. We add more lithium ions, and we get lithium-9 germanium-4, and these are both amorphous. And then we get our crystalline lithium-15 germanium-4, which we knew from diffraction. And then we don't know, because there were a bunch of wiggles that were pretty much noise. But then at the very end, that peak reappeared, and that is from amorphous germanium. So we didn't get crystalline germanium back, but we got amorphous germanium back, which is almost just as good. But we still have a big question mark here, so there's a lot of work left to do. But let's apply what we've learned so far. So we used the 3 different techniques, imaging and the diffraction and spectroscopy, to learn about the morphology changes, what is happening to these particles visually, and also their chemical changes. We know that the smaller particles become inactive in the second cycle. They're not expanding and contracting, and so that's contributing to a capacity loss, which we want to prevent. We also know that the largest particles break up, and they completely fracture into smaller particles, which we also want to prevent. And from the chemistry, we can see what alloys, lithium-germanium alloys, we're creating. And we also know that we start out with crystalline germanium, but we end up with amorphous germanium. And so we don't end up with what we started with, so we're losing capacity there as well. So what do we want to do? How do we want to make our battery better going forward? Well, first we want to use small particles. We want to use small particles because they don't fracture, they don't crack, but they don't stay connected. So we also want to use the self-healing polymer, this glue that's going to keep our small particles together and well connected. And so hopefully with those 2 things, we can design a high-capacity battery, a battery that's going to get us 300 miles to a charge, 400 miles to a charge, and is going to last the lifetime of our car. And those are the 2 things we want. So we're going to improve the range, but not destroy the cycle life, the lifetime of the battery. Now, of course, we still have to work on the price and the charge time, but that's a whole nother talk. So we've made some improvements. And so bringing it all back, why do we want a battery that's going to last longer? It's going to have a higher capacity. Well, we want to be able to use clean energy for our large section. 28% of our energy is consumed by transportation. So we want to be able to convert all of that energy into clean energy. And so we need to really improve this battery technology that's going to go into our cars. And then finally, science is not done alone. I did not do all of this. I had lots of help. Nian Liu, as I said before, he made a lot of these batteries. He's just graduated from Stanford. His principal investigator was Yi Shui, his advisor. Linda Lim, she did the diffraction and also the spectroscopy, and she's a Stanford graduate student as well. And then staff scientists at SLAC, Joy Andrews, Michael Toney, and Eugene Liu also helped. And I want to thank you guys for your attention. Thank you, guys.
Okay, well, thank you very much. There we go. Thank you very much, Joanna. I'm not following my own advice. Let's see if we can make this. Yeah. Okay. Now I'll follow my own advice. My advice is, if you'd like to ask a question, raise your hand, attract the attention of these people out here with the microphones. We're recording this session, so please wait for the microphone before you ask your question. So, who's curious about this?
Well, just in the last, 2 weeks or so, there was an announcement from IBM Research, I think, about self-healing polymers. Does that apply to you, or their examples had nothing to do with batteries, but does that work apply to you?
Naively, I would say yes. I don't know the specific work you're talking about, but the self-healing polymers that the Stanford group, BOW group, is working on was recently published. I don't know where their funding came from, but yeah, any of these polymers that's going to keep everything together, especially if they're good conductors of electrons, that would be even ideal.
Sir.
Okay, you mentioned at the beginning that they had fast recharge for batteries like 15 or 30 minutes, but this wasn't good for the battery. Does X-ray analysis help you towards faster charging of batteries, or is the whole thing a matter of heat dissipation, in which case you need to get a cooling system in the battery, or what is the issue?
Mostly the issue is how quickly can you put lithium ions into a material. So for germanium, for example, oftentimes you only can put in about a third of the lithium ions, and then the battery stops charging. So when it says that it's completely charged, you're really not completely charged.
So it's more than a heat dissipation problem.
More than heat, yes. It also depends on the material. There are some materials that can charge more quickly than other materials, but they often don't have as high a capacity.
Couple of questions. First, you say the small particles become disconnected, so they're no longer active. What makes you think they won't crack if they are connected?
So I didn't really highlight in the movie, but the smallest particles, the ones that were had diameters of about 3 microns or smaller, didn't show any cracks at all as they expanded and contracted. So they can actually expand, contract indefinitely, assuming they stay connected electronically.
And the second question is, are you trying different electrolytes to get the small particles back into contact?
We think it's mostly the polymer matrix that's the issue and not the electrolyte. We haven't done too many experiments on different electrolytes.
You mentioned earlier you chose germanium because it imaged better in the light, but carbon actually would make a better battery. So is this work, if I understood correctly?
Silicon. Silicon would make a better battery.
I'm going the wrong direction. Okay.
Yeah.
Would this work be applicable to those other materials in the same column of the periodic chart?
Some things are and some things aren't. So silicon does actually fracture more easily than germanium. And so now that we've shown it to work, we're actually going to move to silicon and do the same type of experiments with silicon as well. But we believe that what you can see is that even 100 nanometer particles in silicon will fracture. When germanium's, it's 10 times that.
Okay, I had some questions about the CV curves. I noticed during the charging or discharging phase, there was a really large change, like an order of magnitude in the cell potential. And it almost looks like a phase change going on. And that also has a lot, I do electrical engineering, and a lot of, and that kind of voltage variation, it's not impossible to deal with, but it does complicate the power controllers for the motor and the charger.
Yeah.
So do you expect that kind of curve with silicon?
Yes, silicon actually has a lower curve. There's the plateau is down here.
Because there's kind of a perverse reversion that the highest current will have to be drawn near the lowest part of the capacity. And that actually means more heating and things from resistive losses and things.
Yeah.
Do you have any more? Anyway.
So I will mention that this is an anode material, and so most cathode materials have plateaus much higher. And we do want to have the anode have a plateau really low so that we can have a large voltage window.
Oh, okay, I see. The cathode would, I remember my redox tables, there's always a pair.
Yeah, I actually avoided cathode and anode just to simplify things in general.
Yeah, I know they're even reversed in cells versus electroplating.
Yes.
Yeah.
You mentioned that to make a better battery, you would need two things. One, to make sure the particles stay smaller, and the second one, that there's a glue that keeps them together. But from what you explained, it looks like you may also have to make sure that you preserve the crystal, or is that not necessary?
It's not necessary, although one could conceive of starting, instead of starting with crystalline germanium, starting with amorphous germanium, and then you wouldn't have that capacity loss. But the capacity loss from going from crystalline germanium to amorphous is not that large, not compared to losing those particles. So you could start with amorphous germanium, if you would like. You could start with amorphous silicon. Amorphous silicon actually doesn't fracture as much, yeah.
After this, after optimizing, putting every possible optimization to this process, where do we get in that curve leading to the fuel, in that graph? And what's next after that?
So to really go really far in that curve, and I'll show it. To really go far in that curve, we have to go beyond lithium-ion batteries, and that's really the answer. I will get back to the curve. So lithium-ion is really going to keep us in this circle. Maybe go closer to lithium metal, but if we really want to get close to the fossil fuel, we need to think of something completely different. So germanium would solve the problem in 5 years. If we want to solve the problem in 20 to 50 years, most people are looking at lithium air batteries, which is using lithium metal. But we need something creative to fill that gap.
You just answered
Okay.
what I was going to ask.
The question over there.
I've seen a number of other talks of different nanostructures and things that people are working on, and I've seen lots of slides of microscopy. But can you tell us what is different about the synchrotron that other people haven't been able to do with other techniques to look at the ions expanding?
So in terms of microscopy, so just imaging with a microscope, there's 3 main microscopes that you think of. Visible light microscope, which you could not get the resolution. You couldn't see these small particles, the cracks in the small particles if you used a visible light microscope. You also can't see through metal. So our germanium particles are sitting on nickel foil, so you couldn't see through that. The other end, if you want really high resolution images, you would go to an electron microscope, but electron microscopes can only go through a couple hundred nanometers worth of material. So you can design very specialized batteries that would work in an electron microscope, but they're not really realistic. So they're more like the frog in the aquarium rather than the frog in the forest.
Last question,
I'm just curious, how much longer do you have for your funding? What I really mean to ask is
Do you have money?
I wish I did. Sorry. How much of the sort of plan you outlined in terms of going forward do you actually expect to be able to accomplish in your current?
So we have Linda Lim, the graduate student who's worked on some of this, is continuing her PhD work on this, and part of it is extending this beyond. And we have another graduate student also just now starting, and he's going to be focused mostly using the self-healing polymer and also looking at silicon. So we're definitely moving forward with it. After publishing a few papers on looking at real batteries with X-rays, we've actually had a number of companies in the area come and say, we want to use your synchrotron, we want your expertise. So it's being noticed.
Okay, so let's thank Joanna very much. Now, as is usual here, not only will Joanna stay around, but also the people who are holding the microphones are people from her lab, and so they can also answer your questions. So if you'd like to just walk around the room and ask more questions, we're happy to oblige you. And the next one of these will be at the end of July. Speaker to be announced. I'm sorry, but hopefully we'll see you then. Thank you very much.